Alright, in this video we're going to go ahead and relate the whole idea of current to what we learned in the last unit. So again, we talked about the fact that if we hooked a wire up to a battery like this that had like a positive and a negative end, that would cause electrons to flow through the wire. And electrons would go in this direction, and the current is actually opposite of that, which is kind of weird. But really what the battery does is it sets up a uniform electric field within the wire. Now, we learned in the last unit about parallel plates and stuff like that establishing electric fields. Well, the batteries do this as well. So do outlets and things like that. And really what is establishing the uniform electric field is the fact that there is some potential difference. So we have some potential difference from one end to the other, and the potential difference, remember, is given by the unit volts. So sometimes volts is said to be the push or pull on an electron, which really that's force, but we sort of understand the idea that this change in potential from one place to another allows electrons to move. Current is the actual movement of the electrons, and these two items are mathematically related by Ohm's law. However, there's one more variable that's involved in Ohm's law. So we know that electrons are going to move from one place to another, but this material here, when the electrons move, they're not just flying from one side to another. They actually sort of bounce around in there, and there's a net flow, which is what the current ends up being. However, as they're running into things, there's some energy that is lost, and the electron's flow is impeded. We call this resistance. It's where electron flow is impeded, and as the electrons move, some of the energy is lost, and the energy leaves this simple circuit here, and that's how we use these electrical devices, or an electrical current, in order to get energy out and power something, right? To power an electrical device or a motor or something like that. So the relationship between volts and current and resistance is that V is equal to IR. This is Ohm's law, where volts is equal to current, remember, which is amps, times R, which is resistance, and the unit we use is called ohms, why it's called Ohm's law. And we write it with this Greek letter omega. So let's say I plug up into this simple circuit an ammeter. An ammeter is a device that measures current, and let's say that ammeter says I have 2 amps of current. Well, let's figure out what the resistance in the wire is. Alright, so I've got 9 volts is equal to 2 amps times R. So to solve for R, I just divide by 2 on both sides, and I get that the resistance in this circuit is 4.5 ohms. So we're using the movement of electrons through a uniform electric field, and the fact that they have a high potential energy, they move from an area of high potential energy to low potential energy, and that energy leaves in the circuit, and we can harness that energy in order to power things. So when we draw circuits like this, we actually draw something called a schematic. And so I'm going to give you an example of a simple schematic for a simple electric device, and then we'll use Ohm's law in the next video to sort of look at more complicated circuits. So this is the simplest kind of circuit. So let's say I have a lamp like this, and there's a switch, and the lamp is attached to a cord with 2 prongs, right, that goes into an outlet, and there is just a basic light bulb with a filament. Right? So when I plug it up into the outlet, the power outlet, causes the current to flow, the light bulb lights up, and the energy leaves this circuit in the form of both heat and light, right, from the filament, right? So the outlet is where we get our volts. The current is running through the wire, and where the energy leaves the circuit is considered the resistor, so it would be the filament of this light bulb. Now, the switch also can close and open the circuit. So if I were to draw a schematic for this simple device, I draw the source like this. So two little lines. Sometimes they're the same length, sometimes they're different lengths. Sometimes you'll see something a little bit different if it's batteries, but most often you'll see like one or two lines, and that indicates, you know, your voltage source, right? And then I draw the wires that go to the light bulb or resistor. Resistors are usually drawn like this, or a light bulb with a circle around it. And then over here we go, and then we have our switch, and then it comes back to the other side that's plugged into the other side of the wire. Now this circuit is said to be open, right? Which means it's not flowing any electricity. The switch is open here. If I were to close the switch, closing the switch then turns the circuit on and causes current to flow. Now when you look at a schematic, the convention is that the current is flowing clockwise this way, right? So that means electrons would be flowing the opposite direction this way, right? And so we can calculate something out, right? Let's say I've got 120 volts and I have my resistor being like, I don't know, 10 ohms, right? So I know that light bulb has 10 ohms of resistance. I could actually figure out what the current in the circuit is. So you've got 120 volts is equal to I, that's what I'm trying to find, the current, times 10 ohms. And so I would get that the current in this wire is 12 amps, all right? And that as the electrons are flowing through the resistor, which is the light bulb, there is energy leaving in the form of both heat and light. Now, energy is actually, we actually define it as power, and then we'll talk about how that relates to energy, right? So the power that is dissipated from a circuit, that means leaves the circuit, is equal to two things. It is equal to IV, or it's also equal to, P equals I squared R. Both of these can be used to figure out the watts that comes out of this circuit. So let's just go ahead and do that, right? I've got current, I just figured out was 12 amps, and I've got volts, which is 120. So 12 amps times 120 volts. And if I multiply those two out, let me just grab a calculator really quick. That will give me the watts. All right, so I have 1,440 watts. Now, if I did it this way, I should get the same answer, right? So if I did 12 squared times 10, again, 1,440 watts. So this is the power that leaves the circuit. Now, just one last thing is this whole idea of energy, right? So let's just kind of recall that, I'm going to move this over here. Remember we had 1,440 watts. Remember that, which is my power. Remember that power is energy over time. So if I wanted to know, let's say, how much energy left the circuit, well, I would have to know how long it was plugged up for, right, in order to solve this. So let's say I plugged up the circuit or the lamp for like 5 seconds. Let's just figure out how much energy, how many joules came out of this. Well, I would just solve this, and this, that we use the terminology, this is energy dissipated from the circuit. So I would take that 1,440 watts and I would multiply it by the 5 seconds I had the thing on, right? And the answer would be 7,200 joules. So that would be 7,200 joules, right? So in the next unit, I will actually, in the next video, I'll actually talk about when we combine more than one resistor and how to perform calculations with more than one resistor.